Okay, let's unpack this. We talk a lot about scaling laws on this show. We treat them like the golden rules of AI physics. You know, you look at Kaplan or the famous chinchilla laws, and they basically tell you if you make the model this much bigger, feed it this much more data, it'll get exactly this much smarter. It's like gravity.
Right. It's the formula that lets you justify spending, I don't know, $10 billion on a data center. It's the Bible.
Exactly. But here's the thing, and it's a massive elephant in the room. Those laws, they have a huge blind spot. They almost exclusively assume the model is learning English.
It's the English first bias. And it is a huge problem because the math that works for English, it just doesn't work when you try to cram, say, 50 languages into the same neural network.
As the gravity stops working.
The math completely breaks down. If you apply those same rules to a model trying to learn Swahili, Hindi, and German all at once, yeah, it all falls apart.
So today we are diving into a paper that finally attempts to fix the physics. It's called ATS, Adaptive Transfer Scaling Laws. And honestly, this feels like a landmark moment.
It really is significant.
We're talking about the first real scientific attempt to break the English monopoly on AI architecture.
And to understand why, you just have to look at the sheer scale of the work they did. This wasn't a simulation. Their researchers ran 774 independent training experiments.
That number blew my mind. 774. I mean, usually you see a paper with, what, a dozen runs?
Right, because training these things is unbelievably expensive. But they went all out. They trained models from tiny 10 million parameter versions all the way up to 8 billion. They used the MADLAD 400 dataset, so over 400 training languages, and evaluated on 48.
They just brute force the science of it.
They did. They did the homework, so we don't have to. We're moving from, intuition, just guessing that maybe Spanish helps Italian, to actual precise formulas.
Okay, so the mission for this deep dive is to figure out exactly how to build a model that understands the world, not just the internet's English corner. But to do that, we have to start with a concept from the paper that sounds like a D&D curse. The curse of multilinguality.
It sounds dramatic, but for a systems architect, it is a nightmare.
So what is this curse? Is the model, haunted?
In a way, yeah. It's haunted by limited capacity. The curse of multilinguality is this phenomenon where if you have a model of a fixed size, a set number of neurons, adding more languages to the training mix actually makes the model worse at each individual language.
It feels so counterintuitive. You'd think, hey, it's learning more stuff, it's getting smarter. But you're saying if I have a model that's great at French, and then I force it to learn German and Chinese too, its French skills actually get worse.
Precisely. Think of the model's parameters as a limited budget. When it's just learning French, 100% of that budget goes to French. But every time you add another language, you're taxing that budget. You're forcing the same neurons to store new grammar rules, new vocab.
It's capacity contention. They're all fighting for the same piece of the pie.
Exactly. And the researchers wanted to quantify this. They looked at 3 main variables: $, the model size, the amount of data, and $, the number of languages.
N, D, and K. Okay. And which one is the villain here?
Oh, it's $, the number of languages, by a long shot. They found that $, has a far greater negative impact on the loss than the other factors. The research shows that relative loss just turnabout, it grows monotonically as $, increases.
Monotonically. So it just keeps going up. There's no free lunch where you add a 10th language and suddenly it gets easier.
Nope. It's a relentless tax. And this is crucial for developers. The capacity constraint is the bottleneck. You might think, oh, I'll just throw more data at it.
So more flashcards.
Exactly. But the paper shows that's super inefficient. Increasing the model size, the knowledge giving it a bigger brain, delivers much larger marginal gains than just adding more total tokens. If you're drowning in languages, you need a bigger boat, not just more time in the water.
You're going to need a bigger boat. Like that. So just adding data hits, diminishing returns fast, but adding parameters helps absorb that curse.
Correct. But here's where it gets really nuanced. It's not just a curse. There is a silver lining, because languages aren't just random noise. They share structures.
And this brings us to the part of the paper I just found so cool to look at, the cross-lingual transfer matrix.
This is the crown jewel of the study, I think. It's a 38 by 38 grid where they measured the relationship between 1,444 different language pair.
It's basically a friendship chart for languages. Who helps whom and who hurts whom.
Exactly. They measured transfer versus interference. Positive transfer means training on language A actually lowers the loss, so it improves performance on language B. Interference is the opposite. A confuses the model about B.
So looking at this map, what's the biggest predictor of a good friendship? Is it grammar, Geography,
It's simpler. Script is king.
the alphabet itself.
Yes. Empirically, sharing a script like Latin to Latin is the single strongest predictor of positive transfer. The moment you try to mix scripts, say English and Latin script and Russian and Cyrillic, the transfer scores just plummet.
What are the numbers on that? How big is the gap?
It's massive. They found a transfer score of about negative 0.23 for different languages that share the same script. But if you mix scripts, that negative score drops all the way to negative 0.39.
Wow. So nearly double the interference just because the letters look different.
Well, it makes sense, right? These models process tokens. If the model has to learn an entirely new set of characters, like Chinese logograms versus Latin letters, it burns a huge amount of its capacity just learning to read before it can even get to the meaning.
It's like trying to learn history, but the textbook is in a secret code you have to crack first.
That's a great way to put it. And, obviously language family plays a huge role too. Romance languages help other Romance languages. But there is a twist in the data that I found really compelling. The asymmetry.
Ah, the unrequited love section of the deep dive.
It really is. We tend to assume transfer is a two-way street. If Spanish helps French, surely French helps Spanish back.
Right. Symmetry.
And for highly related languages, that's true. Spanish and French, Russian and Ukrainian, they're symmetric. They help each other out. But outside of those tight families, transfer is often not reciprocal at all. Just because language A helps language B doesn't mean B helps A.
So who are the givers and who are the takers?
Well, the data really corroborates this idea of altruistic languages. These are high-resource languages that help tons of other languages learn, but they don't get much help back in return.
And let me guess, the biggest altruist is English.
It is. English, French, Spanish, and surprisingly Hebrew are highlighted as top helper languages. If you train a model on English, it generally helps it understand the structural logic of other languages. But those other languages don't really help the model get better at English.
So English is doing all the heavy lifting and getting zero credit. What about the opposite? Are there languages that are just, I don't know, toxic?
Isolates is the term they use. They found that low-resource languages like Urdu or Pashto often show significant negative transfer. They interfere with others, and others interfere with them.
So if you're building a multilingual model, adding Urdu isn't just a nice-to-have. It's actually a tax on the system's intelligence.
It is a tax you have to account for, which leads us perfectly into the next big concept, the compute efficiency tax.
I assume this isn't something I pay to the government.
No, you pay it in GPUs. The compute efficiency tax is the cost of generalization. The paper is really clear. A dedicated specialist is almost always more efficient than a generalist.
So a model that only speaks English will always beat a multilingual model at English, assuming they're the same size.
Yes. But the tax isn't distributed equally, and this brings us right back to the English bias. English specifically suffers the highest compute efficiency tax in a multilingual setting.
Because it's the altruist.
Exactly. Because English is so resource-rich, it benefits less from transfer than other languages benefit from it. It's the anchor. So when you dilute its capacity with 40 other languages, English performance drops, and it gets almost nothing back to compensate.
So English takes one for the team. But what about the languages that don't have as much data? Like Swahili or Hindi, do they pay a tax?
They face a different problem, maybe even worse. The researchers found that for languages like Hindi and Swahili, the scaling curves eventually bend upward.
Bending upward is bad. We want the loss line going down.
Correct. The curve bends up because of severe data repetition. There just isn't enough unique text data in Swahili compared to English, so the model starts seeing the same sentences over and over and over.
Yeah, it is memorizing at that point.
It overfits, and this is where the ATLS scaling law really beats the old chinchilla laws. Chinchilla just saw data as one big blob. ATLS splits it. It separates data into 3 buckets: monolingual target data, transfer language data, and then just other language data.
Okay, so Chinchilla says all tokens are created equal. ATLS says no, this token is helpful transfer and this token is just noise.
Roughly, yeah. By weighing these buckets differently, ATLAs can predict performance way, way better on unseen language mixtures. It quantifies how much help the target language is getting from its neighbors to offset that lack of data.
So let's get practical. I'm a developer listening to this.
Yeah.
I have a boss who says, we have a model that knows 10 languages. We need to scale to 40. And you can't make the model dumber.
The developer's dilemma: do more with. Well, you have to spend more.
Right. So what do I do? What does the paper say?
This paper gives you the formula called the ISO loss frontier. It tells you exactly how much you need to increase your compute budget to expand your language coverage without losing quality.
I love that we have a formula now. No more guessing. So walk me through it. I'm quadrupling my languages from K to 4K. What's the damage?
The rule of thumb is that your compute budget needs to increase by roughly $2 to the power of 0.97.
Okay, $2 is the multiplier, so 4 to the power of 0.97 is pretty much 4.
Roughly linear, yes. But here's the secret sauce: how you spend that budget. To keep the quality the same, the paper says you need to increase your total training tokens, DAS $2.74 times, and your model size 9.4 times.
Wait, let's do the math there. I have 4 times as many languages, but I'm only using 2.74 times as much total data. Doesn't that mean
Yes.
I'm using less data for each language?
You absolutely are. That is the wild counterintuitive insight. In that 4x example, you end up using about 32% less data per specific language.
How is that possible? If I study French 32% less, I should get worse at French.
You would be if you were studying in a vacuum. But remember the matrix. Remember the transfer. Because you added those 30 other languages, the positive transfer effects, the friendship bonuses, they compensate for the reduced data.
That is incredibly cool. The crowd supports the individual.
It validates the entire concept of multilingual training. It proves that the model is learning the idea of language, which makes it more efficient at learning any specific one.
Okay, so that handles scaling. But there's another big developer question. The lazy approach versus the hard work approach.
To pre-train or to fine-tune? The eternal question.
Right. So there are these massive Unimax checkpoints out there already trained on everything. Do I just fine-tune one of those, or do I build my own artisanal farm-to-table model from scratch?
The answer, as always in engineering, is it depends on your budget. But ATLAs finally gives us the specific numbers.
Lay it on me.
If you have a smaller budget, fine-tuning wins. Hands down, you get a head start because the Unimax model already understands basic syntax and structure. But there is a crossover point.
The moment where the hard work pays off.
Exactly. If your budget allows you to train for more than roughly 283 billion tokens, pre-training from scratch will eventually give you a better result.
283 billion tokens. That's the magic number.
That's the upper bound. The crossover happens somewhere between 144 billion and 283 billion tokens. It depends on the language.
Why does the from-scratch model win eventually? Shouldn't that head start always help?
You'd think so. But generalist models have baggage. They're optimized for everything, which means they aren't perfectly optimized for your specific thing. It's a kind of negative interference or even forgetting.
So a specialist will beat the generalist if you give them enough time.
Right. If you take a model that knows 100 languages and force it to focus on just one, it has to fight against its own generalist nature. A model that has done nothing but focus on your target from day one will eventually surpass it, with one major exception.
Let me guess. English.
English.
Why does English always break the rules?
English pre-training converges fastest from scratch. It beats the fine-tuning route much, much earlier. Part of that is just because English makes up a huge chunk, about 5% of the Unimax mixture they used, compared to like 1.4% for other languages.
Yep.
It's just the dominant force in the training data.
It feels like English plays by a different set of physics in this entire paper.
Yeah.
It's the altruist, it pays the highest tax, it converges differently.
It is an outlier in almost every metric, yeah.
So let's bring this all back together. We started with the curse of multilinguality, this idea that adding languages breaks the model. But what ATLA shows is that it's not a curse, it's just a math problem we hadn't solved yet.
Exactly. We've gone from English-first scaling laws, which were totally blind to these dynamics, to adaptive transfer laws. We now know, yes, there's a capacity cost, but we can calculate it. We know there's transfer, and we can measure it with that 38 by 38 matrix.
And most importantly for the people building this stuff, we have the isolos frontier. We know exactly how big our boat needs to be if we want to add more passengers without sinking.
It provides the scientific confidence to actually build these things at scale. If you really want to democratize AI, you can't just hope the model magically figures out Urdu. You have to engineer the capacity for it.
It's fascinating, but I keep coming back to that altruistic language concept you mentioned. English helps everyone, but nobody really helps English.
It is a provocative thought to leave on, isn't it?
Right, because if English is the universal donor, the O-negative blood type of AI, what does that mean for the future? Are we doomed to always build these massive feeder models in English just to bootstrap the rest of the world?
It raises a real structural question. If the architecture inherently relies on a high-resource anchor language to stabilize the others, Are we actually reinforcing the English monopoly while we're trying to break it?
Wow.
Are we building a multilingual future that is still, at its very core, dependent on English data to even function?
That is a deep thought for the drive home. We might be democratizing the output, but the engine is still running on English fuel.
And until we find another altruistic anchor or figure out how to make low-resource languages synergize better without English, that might just be the reality for a while.
Well, on that note, thanks for listening to this deep dive into ATLAs. Hopefully, your next model training run is a little less cursed. We'll catch you on the next one.
Thanks for listening.